Okay, so how are you? Good?
Wait, sir.
Yes?
Course coded for again. You have to know it.
KAN. It's,
No, it's yes.
anyways, alright. I don't know what the course code for kin is. So ladies, we started the unit on diversity. Okay, so so it's all about looking at groups of things, groups of organisms. And one of the first groups we'll look at are a group called viruses, okay? So why do I have a picture of a flower? Is old man Barry getting confused? Has he mixed up his plant presentation with his virus presentation? What do you think the answer to that question is? Olivia, what do you think? No? So what is this picture of a flower have to do with viruses? So how many of you noticed the streak pattern in the flower? Okay, that's actually caused by a virus. Don't ask me the name of the virus, I don't remember. Okay. The point is that we're going to talk about viruses, and I want you to understand that there are more viruses in the world than there are cells. And a virus's job is to hijack a cell and make that cell make more copies of the virus. So it doesn't have to be animal cells. I know we're all familiar with viruses that attack us, but, plants, even bacteria, fungi, they all are susceptible to viruses. So we're going to talk about viruses, okay? Now, viruses are quite simple. They're basically two things, okay? And then there's even a stripped-down version of a virus called a virion, which is only one of these two things. I'll explain this in a second. So a virus is really just a genome, so it's genetics, plus a coat made of protein. So here is the avian flu. All right, this one is quite a nasty virus. The mortality rate from this virus is over 30%, as high as 50 to 60%. I've heard. But think about catching a virus, and there's a 1 in 3 chance or better that it will kill you. That's pretty scary. And I'm not making this stuff up. This virus right now can get from animal into person, but has not been able to figure out person-to-person transmission. So for now, we're pretty lucky. Okay, pretty lucky. But basically, this virus is simply a protein coat, and inside the virus is a genome. Now, I believe this one is an RNA genome. Okay, this is the tobacco mosaic virus. Again, it's just a protein coat. This one attacks the tobacco plant. And you can see it's an RNA genome with a protein coat. This is the adenovirus. Now, they have some pretty interesting shapes. This kind of looks like something you would hang on a Christmas tree. Okay. This next one is a virus that attacks bacteria, called the Bacteriophage. Okay. Looks almost like a spider. Again, it's just a protein coat. Now, this genome is actually a DNA. Okay, so DNA genome. Now, viruses are things that I don't consider them living, okay? Because they cannot really replicate on their own. So what they need to do is they need to find a cell, infect it, and basically make that cell make more copies of it. Now, there's two types of viruses, okay, that we know of, DNA and RNA viruses. So, because the big theme about this unit is being able to classify and group things, compare them. DNA viruses are things like this. So this is a type of virus that gives you smallpox. Now, smallpox, should be in the box. Okay, smallpox. I don't know if you know the story of smallpox. Was actually eradicated. I believe it was the early 80s. In the 70s, they started this mass vaccination campaign around the world where hundreds of thousands of people got together to basically vaccinate against smallpox, because smallpox was pretty devastating. Very high mortality rate, very high infectious rate, and in the 80s, there was one last case of smallpox. So it's been eradicated. So I mean, when you get vaccinated, right, there are some things that you get vaccinated for. So what would be an example of something you get vaccinated for? Okay, HPV. But isn't that when you're older? Okay, but what about when you're young? Like a baby. Yeah, now some of those are bacterial. So there's bacterial meningitis. I believe that one's against bacteria. There's hepatitis vaccines. That's virus. Tetanus is bacteria, yes. Yeah. How about chickenpox? You get vaccinated? Did you say that? Now, you don't probably get vaccinated as a baby against the flu virus, I don't think, but you do get as an adult. Some of you may get the flu vaccine. Okay. Anyone here been vaccinated against smallpox? You have? When? No. No. The chicken, believe me, it's not the same. The risk of you dying from the chickenpox is very, very small. It's under 1%. I don't know what the exact, it's like a fraction of a percent. Smallpox had like a mortality rate of like 20, 30%. So very, very deadly. Yep. Shingles is the chickenpox virus that will come back in adult form. And it's pretty, I've never had it, but apparently it's very painful. Yes, you can. Yeah. Yep. Then you get vaccines for the measles, right. And that's a virus. Now, this virus is a DNA virus, okay? Now, the thing about the difference between a virus like this and some other viruses, can you give me an example of a virus that you need constant immunization for?
Flu.
Right. So the flu virus is something that requires immunization every year, right? Whereas, how many times have you been immunized against chickenpox? Once. There's two types. Now, there's a reason why. Because there's two types of viruses, one type is very stable. It's the DNA one is very stable because it has a spell check. I'm going to call it a spell check. When it replicates, it checks for mistakes. So the odds of it mutating are very, very low. Now, from an evolutionary point of view, that's good on the one hand and bad on the other hand, right? It's good on the one hand because if the virus is successful, you don't really want to make too much change. But it's bad on the other hand because it does not generate as much variety as you possibly can. So, an RNA virus does not check for mistakes as much. So what happens when it makes copies, there are tons of mistakes. Now, you know, the more mistakes you make, the more likely it is that you might come across a mutation that produces something favorable for the virus. So what happens is, and I'm not saying the greater the mutation rate, the better it is, because most mistakes are bad. But if you are a stable virus, the reason why you only need to be vaccinated once is because chances are the virus hasn't really changed. So if the vaccine worked as a baby, probably when you encounter the virus as a 20-year-old or a 40-year-old, it probably hasn't changed much. The flu virus, however, mutates frequently. So if you get vaccinated and then you come across, let's say, you get vaccinated in 2014, in 2015 there might be a different form that comes out, or 2006, because it's changing. It's not very unstable. So there's a trade-off between being stable and being unstable. Don't ask me which one's better, because I think you know the answer by now. Okay, it depends, right? It should depend. Okay.
Question.
Yes.
How much does a protein coat cost? Is it warm?
Bye, Alexa.
Bio. Sorry.
That's a good joke.
What she said before?
What's that?
She's like, there was a band called Chickenpox, and they just came out with the new Shingles.
Wow. Alright, so, now, see ya. Good luck. I'll see you guys. Alright. Hold on. Let me pause it. Okay, so, alright. So I said every virus needs to be able to hijack a cell. So in this picture, you're actually seeing that. Okay, so here is a picture of a bacterium, which is our next group we'll be looking at in diversity. Okay, and you can see that there are, I think we see, what is it, 7 here, virus, call them virus particles. Okay, and there are, you can see some of them have actually attached themselves to the virus. And you see this little strand that's, looks like it's getting into the cell. That's the genome of the virus. So what has to happen for a virus to hijack a cell? Either the virus has to get into the cell, or at the very least, its genome has to get in. So when that genome gets into the cell, it will reprogram the cell to make more copies of it. So this is the way it works. So what I'm going to show you is something called a lytic cycle. This is what happens when you get an infection and then you start seeing symptoms right away. So for example, here is a virus attaching itself to a cell. So it's got to be able to attach. Then either the genome or the virus has to get in. So it's got to be penetration, followed by replication. The replication this is what the cell does. The cell gets reprogrammed, and it makes copies of the viral genome, and it makes copies of the protein coat. Remember, because it's made of 2 parts, right? A genome and a coat. And then you have an assembly. So the coat and the genome are put together. And then the release. This is where you start getting sick, because you can see in this picture that the cells that are infected will what? They'll die. Okay? And that actually triggers your immune system. When the cells die, they release chemicals, triggers your immune system, and then you start seeing symptoms. This is pretty quick. You get the infection, the virus enters, and then you start seeing symptoms a few days later. That's cells undergoing the lytic cycle. What would be an example of a virus that you get, and then you'll see symptoms a few days later?
Wait, pardon me?
An example of a virus that you could get, and you'll see symptoms a few days later. Yeah, so the bird flu would be one that you would get quickly. Any type of flu, the cold. Those are examples of viruses that you'll get them, and then you'll start to see symptoms. Start seeing symptoms right away.
Why did you give me that look? That's totally true.
That's an infection. That's different.
Oh.
Okay. Okay. Here's one, the Ebola virus. How many of you have heard of the Ebola virus? It was very famous last year. It's been around for a while. It's been around, at least that we know of, since the 70s. And this virus has very high mortality rate. I've heard numbers as high as 90%. Imagine getting a virus and there's a 9 in 10 chance that you'll die. So, this one, again, you contract it. Do you remember all the scares from last year?
The what?
The scares.
About the Africans coming in?
Well, people visiting Africa and coming back, and people getting, a man who recently visited Africa is sick in the hospital, and you would have all of these, reports, right? Because this is a very scary virus. Very scary. And I can understand why people would be terrified. And I can understand why it would get into the news pretty quickly. I just said, if you're paying attention, that there's a 90% chance mortality rate if you contract it.
But how do you do it?
Okay, coming in close contact with bodily fluids. So if you have someone who's infected, touching them, coming in very close contact, it's not spread through sneezing or coughing. its contact with their fluids.
If the public watching and somebody pees on the couch,
No,
and
it's
it
no,
counts?
no.
Does that count?
This is the breakdown of the virus in terms of its, and we will talk about actually how to classify organisms. I haven't talked to you about that yet. Okay. So we will talk about how organisms are classified. So I'm going to come back to this, not today, but some other point. Yep. That's a picture of the virus. That picture is this picture. It's just, nope, that's, guys, you guys okay today? That's the virus, okay? Yes. Yes. Well, as you probably noticed from the other pictures, these viruses have very different shapes. Okay? So they're very unusual. And this one happens to look like some gummy string or whatever you guys eat. Now, sometimes a virus does not reveal itself right away. Sometimes what happens is the virus undergoes a different, so it doesn't undergo lytic right away. So lytic, again, is when the virus gets in, starts replicating, and the cells burst. Right, Dana? Lysogenic is when the virus gets in, and what happens is the genome gets in, so you can see right here, the virus is attached, the genome is penetrated, but the genome gets integrated. Now, this is different because what happens now is when that cell makes a copy of itself through cell division, the genome of the virus gets copied along with it. So the cells will divide, and the virus is dormant. It's doing nothing. But at some point, the virus will then switch to this form of reproduction, the lytic cycle. So all viruses will go lytic, but some will start off as lysogenic first. So if they go lysogenic first, that means they're going to go dormant for at least a few months, maybe years. What would be an example of a virus that would first integrate itself and you wouldn't even notice you had it? Yeah, HIV. Or this one, this is the Herpes Simplex virus. Okay. So the Herpes Simplex virus or the HIV virus, you don't notice it right away. Okay? You notice it after.
When it's too late.
Okay. So again, two dramatically different strategies from a viral point of view. Which one is better? Again, the Ebola virus is like fast and furious, right? It wants to reproduce very aggressively, very quickly, whereas HIV wants to spread pretty slowly over a longer period of time. Obviously, which strategy, it depends on the circumstance. The thing about spreading quickly is if you know there's a viral outbreak and symptoms show up pretty quickly, if you're early enough, you can kind of isolate it and stop it. And that's why they were so adamant, people leaving Africa, setting up zones around areas that have outbreaks to prevent the spread. The problem is once it starts to spread, fast reproducing viruses will explode. Think about the swine flu of 2009. It started off with a single case in Mexico, and then a few weeks later it was worldwide. Now that virus wasn't as dangerous as they thought. I don't know if you remember the whole fear around it. I will talk to you about the fear, not today. The fear probably revolves more around its name. Its name is H1N1. And we'll talk about why it's named H1N1, but not today, okay? And I don't know if you know what H1N1 refers to, but it refers to a virus. Well, I'll explain later on. It has to do with two types of genes in the virus. One is called the H gene, the other one's called the N gene. But the H1N1 is the same virus that killed about 50 million people in World War I. Obviously, the swine flu is not the same virus, even though it's categorized as H1N1. Okay. So it is different, but it's similar. Okay. So here's the thing. For a virus to get in, it has to be able to attach itself. Here you're seeing a picture of that. So here is a virus that has to be able to recognize some protein on the surface of the cell. So in other words, viruses are very specific. It's very unlikely, I'm not saying impossible, very unlikely that the virus gets into birds or some other animal, that it will get into you. So if your dog is sick, chances are that it should not get into you because, what's sitting on the surface of our cells is probably not the same. However, it can happen. Okay? It can happen. It happened in my house. We got sick. Everyone got sick. Even the dog got sick. Exact same. I can't remember what it was, but it was pretty bad. And then I recovered. Then I got the vet bill. And I got sick again after I saw the vet bill. Flu. We actually get our flu virus. It originates from birds. So yeah, it can cross over. Okay? But viruses are very specific. Not only do they target specific organisms, but they target specific cells. So, for example, hepatitis attacks what cells? What cells are attacked by hepatitis virus?
Hepatitis?
Yeah. The virus that causes hepatitis attacks your hepatocytes. Hepatocytes are liver cells. Okay? The HIV virus attacks your white blood cells. Okay? So what it's looking for is a specific protein on the surface of that cell to be able to attach itself to. Once it attaches, the virus gets brought in. So here you're seeing it actually getting brought in. Then the virus will start to replicate, make copies of itself, and escape. So it has to be brought in. Okay? Now, that's important. Because if a virus is sweeping across a population, if you have a mutation that gives those surface proteins a different look, it might give you immunity. We've talked about this with our next one, HIV. So how HIV gets in is the same way all viruses get in. They have to look for a specific protein on the surface of a cell. Here's the thing. If you have a mutation in that protein, it could give you resistance. Do you remember the name of the mutation that gives people HIV resistance? CCR5 mutation, right? That's a mutation in a protein that's supposed to sit in the surface of the cell, and it changes it. Changes it in such a way that the virus can no longer get in. I use this analogy a lot. Think of the virus as having a code, and the code, all of these are like keys. These are the locks. Now the proteins being the locks are encoded in the genome. You change the genome, you could change the lock. So if you have a mutation that changes the lock, that could prevent the key from working. Okay? And therefore the virus won't get in. Of course, the virus can mutate. Right? The virus, because it's coevolution, right? You could mutate to give you resistance, but the virus could also mutate too. And we saw that as an example with the parasite that causes malaria. So here's the thing about HIV. HIV is we talked about DNA viruses are stable, and then RNA viruses are not stable. HIV is not the most, but one of the most unstable viruses. It changes dramatically. That's why it's been very difficult to come up with a drug that can get rid of it, because it's constantly mutating. The reason why it changes so much is because of what it does. So when it gets into a cell, so here it is right here. So here's that virus getting in. Okay. Gets in here. Now, its genome is an RNA genome. Now we talked about this. Your genome is made of what? It's DNA, right? It's a different language. The RNA genome from HIV actually gets converted into DNA. You've seen that in this picture. The DNA is this blue. The RNA is the red. What happens then is the HIV RNA genome gets converted into a DNA genome, and then it gets inserted into a cell's nucleus. So now all of a sudden you have these white blood cells that have been infected, but no one knows anything is going on because the virus isn't attacking. All it's doing is inserting its genome. This process is called reverse transcription. You'll learn in grade 12 that transcription is the process of going from DNA to RNA. Reverse transcription is the process of going from RNA to DNA. It's the opposite. For some reason, after about 8 to 10 years, something triggers the lytic cycle. So first it's going lysogenic, and then it goes lytic. Now, what the triggers, I don't know. I have no idea. But after about 8 to 10 years on average, the virus goes from dormant to active. The genome is converted back to RNA. The RNA genome is copied. The protein code is copied. It's assembled, and then it's released. By that point, there are so many white blood cells that have been infected that the war is almost over unless you get medical intervention. So what's going to happen is your white blood cell count will go down. Now, why is that a problem? What are the white blood cells? Right? That's your immune system. So the thing about HIV, it doesn't kill you. What it does is it kills your immune system, and then some other bacterial virus that is normally safe will kill you because your immune system can't deal with it. Now, luckily now we have a lot of drugs that will slow down the virus. In the 80s, if you contracted HIV, it was a death sentence. Now you have people that have had it for 15, 20 years. I don't know if you know who Magic Johnson is. The basketball player, former basketball player. He's had it, I can't remember, it's been at least, I would imagine, 15 years. He's said that he's had it. And he's still around, doing well. So there's a lot of medication that will slow down the virus. Okay. Alright, so that's it. We talked about viruses. We talked about the different types of viruses, DNA versus RNA. We talked about the lytic versus lysogenic cycle. We talked about some examples of viruses. Do you have questions about viruses? The lytic cycle is this cycle where the virus gets in and starts reproducing. So it gets in, right? Gets in, starts reproducing, and then gets released. How is that different than the lysogenic cycle? Right, it's dormant. What it does is it gets in, but it's not really reproducing. It's just inserting its genome, and as the cells get copied, the instructions for the virus get copied with it. But it's not doing any, it's not killing the cell yet. Then it switches. Then it goes lytic. Okay? So lytic is when the virus is, making copies of itself, assembling itself. I shouldn't say itself. It's the cells that are doing it. And and then they come out of the cell. Whereas lysogenic, it's just spreading with the cells. It's not killing the cell. Okay. Any other questions? Yeah. No, frostbite is it's not a bite. It's when it's too cold, and it's basically like damage to your skin because it's too cold. Yeah, but that's caused by your own cells. Now there are viruses that can trigger cancer, but That's your own cells going crazy on you. Okay? So let's stop it here. The end.